Hey there, it's Mho from Life Mastery. Hope you're having a wonderful day today. Thanks for joining me again as we go through another Chem Phys passage on urea analysis. So the way that this passage dissection is going to work is first I'll go through the passage with you, and rather than just reading it word for word, I'll try to focus on the phrases and the words that I think are most important and that I think might help you when it comes to the questions later on. And when we do come to the questions, then we'll go through each question one by one, step by step, and try to figure out why the correct answers are correct and why the incorrect answers are wrong. And hopefully by the end of this, you'll have a really good understanding of this passage and some concrete strategies that you can take and apply to other MCAT passages that you might be working on at the moment. So yeah, without further ado, let's just get into it. Okay, so why don't we look over this first paragraph together? So, seems to be something about urea monitoring. Okay, so we know that urea monitoring is important for clinical diagnostics, blah, 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 something about the kidney. This is a great way to test drugs. So once again, a typical introduction sentence, just getting us into the frame of the passage and understanding that, okay, we're going to be talking about probably how to analyze urea in this passage. So just in case you didn't already know, urea is a byproduct of protein metabolism. And if you have a lot of urea in the blood, just hyperuricemia, right? That's associated with renal dysfunction. So bad thing, right? So basically, if you have to make a quick summary, too much urea is bad. And honestly, that's a level of understanding that you often just need from the introductory paragraph. So just take with that and roll with it. And commonly used methods for urea determination are based on enzymatic and chemical assays. And we can already see that the next section is going to be titled enzymatic methods. So from this paragraph, we should already have an understanding that this passage is going to be about urea analysis, and more specifically, enzymatic and chemical assays. And why are we looking at urea? Because if you have too much urea in the blood, that can be a bad thing for your kidneys. That's it. So now that we have a good understanding of that, why don't we go into the next paragraph? Okay, so but let's keep reading. Enzymatic methods involve the use of urease on isolated and live cell samples, blah, blah, blah. So that breaks down ammonia and carbon dioxide. Okay, so basically what we have here is that if you use urease on, so it's not the cells in the cells, right? But you extract the cells from the body, isolate and lyse them. So basically break them apart, and whatever's inside the cell, then you can analyze that. So one way you can do that is with this enzymatic method, and that's using this enzyme known as urease, right? So you should be able to tell that it's an enzyme because it has the ase ending. They don't always tell you that, it uses the enzyme called urease. You should be able to assume that from the fact that it's an enzymatic method and this is an ase, right? So we have here that it's a two-step mechanism. The first step is the breakdown of urea to ammonia and carbamate, and then there's a rapid and spontaneous decomposition, releasing heat energy. Okay, so that's already a bit of a hint. They wouldn't mention this if there was no reason for it. So first is the breakdown, and then there's a second step where we release heat and it's spontaneous. So, okay, seems like it's a reaction that is overall spontaneous, right? It doesn't really require us to put in outside energy in order for it to happen. So that also makes it very useful, because if you have it in a enzymatic method like this, right, to test the level of urea using this urease enzyme, you can just add the enzyme and then it'll automatically go into the reaction for you. And in the end, you can then measure the produced ammonia through a pH indicator, ATP, or H2O2. But the more important thing is that you're measuring the ammonia, right? So basically, in this reaction, right, now we can go to figure 1. In this two-step reaction, the end product is basically ammonia. And from the level of ammonia, we can sort of guess the level of urea, okay? And that's kind of the whole gist of this method right there. Okay, so and just when you're seeing reactions in a figure, right, the most important thing is not to try to analyze the whole mechanism, rather just focus on, okay, what's going in, what's coming out, and maybe what's going on in between. Is there like a general sort of label I can give this reaction? Is it a substitution? Is it an oxidation? Is it a reduction? Something like that is honestly usually enough for the questions. If the question requires more of a in-depth understanding of the reaction, then you can give that time to it when the question demands. But more often than not, it'll be like what sort of reactions happening in figure 1? Substitution, reduction, oxidation, acid base. So for this reason, really just try to get an overall picture, like the general idea of what the reaction is what reaction is happening here specifically. And here it seems like, as far as I can tell, that the NH2 is being kind of replaced by the H2O. So it seems to be some sort of substitution reaction, not a classical substitution, of course, because this is not your typical carbon that with the leaving group, and NH2 is not the best leaving group in anything, but you know that around carbonyls like this, you can often have sort of a nucleophile attack leading to the release of another group. So anyway, in general, carbonyls are a great place for organic chemistry to happen. But you don't really need to know the specifics of what the reaction is, right? Just in general, you should be able to tell that one of the NH2s is basically being replaced by this water, and that's thanks to urease, right? That enables that reaction. So that is lowering the activation energy for this, that maybe this part of the reaction isn't actually necessarily spontaneous, or would be spontaneous, but needs just a bit of help from urease in order to happen. Okay, and then the next step ultimately releases carbon dioxide and ammonia. So this is the spontaneous decomposition, right? That's what decomposition is when a compound breaks out into its constituent parts. And you can already see here, this is actually the CO2, COO2, right? So that's CO2, and over here is the NH2. So we can imagine that basically this molecule splits, and we're left with this. And all the atoms in the end are the same as well, right? The H's are balanced, those are balanced. So that's kind of what's happening there. Okay, so yeah, let's go on to the next paragraph then. So in this paragraph, we see that researchers have developed a new reagent combining OPA. So notice that I don't really care about the name. It's better to just go with the acronyms when they give it to you. So this is the chemical assay. So they combine OPA with primaquine, and they compared it to OPA by itself. Okay, so this was the new reagent, right? So OPA with this other thing called primaquine rather than what OPA normally does. Okay, so then they looked at calibration curves, right? So these are a specific type of figure that you should be familiar with, especially when it comes to Phys. And in the Phys section, you see these a lot when it comes to absorbance, right? So in this case, we are looking at something called optical density. So it's just another way to say absorbance. And we're looking at OPA primaquine versus OPA, right? At 430 versus 505. And here, that's made quite clear in the figure. Okay, so let's see what we can get out of this figure. So figure 2a, we see, remember, this is the one with OPA and primaquine. And one thing when it comes to these figures, maybe just in general, right, is rather than taking the time to analyze everything, there's just a couple of things you should notice. And once again, try to get the bigger picture from it. So what are the things that pop out to you, that stand out to you, that you think might be asked about later, right? Try to find the significant result that's resulting from that figure rather than looking for all the nuance. And here, in order to start, right, we notice that on the x-axis, so the independent variable is the urea concentration. So as we go this way, we're increasing the amount of urea, probably in the sample, right, that we're looking at. On the left, is this dependent variable, so the optical density or the absorbance, and we notice that as the urea concentration increases in general, that the absorbance increases, and that makes sense, right? Because what is doing the absorbing is actually the urea and the combination of that within this, with the OPA primaquine or with the OPA alone. So basically, the more urea, the more absorbance that you're going to have. But the key thing is try to figure out the difference between these graphs, because this is really the question of the study, right? This is the hypothesis. The researchers have developed a new reagent that has OPA with primaquine rather than OPA alone. So you should try to figure out, okay, what is the difference between these two? And if you look generally, you see that this slope is quite nice. In fact, you have an R squared of 1, which is very, very rare in research. On the other hand, you have this one, which is just the OPA alone, and you can see that the slope is very, very meager, right? With a equivalent increase of urea concentration, right, let's say from 0 to 4, you have a much lower concentration, or absorbance, I should say. in the OPA alone condition versus the OPA with permethrin. So overall, what that should suggest to you is that this new reagent is actually quite good at visualizing urea. And why that's good is that if you have 4 milligrams, right, sometimes it's super difficult to tell the difference between what here is maybe like 0.3 and 0.27 or something, but this makes the differences between the different concentrations very clear. So overall, this would give you a more accurate estimate. And we also notice that we have 2 curves here, right? H2O versus phenol red. And in general, the phenol red is always less than the H2O, but in this, in the OPA alone condition, it basically overlaps. So that's probably a bad thing, right? Here we see that it's quite separate, and that's probably intentional. Now, I can't say exactly what phenol red is and why they've included it, but the bigger picture is that you just see the trends, right? So if I were to give this to maybe someone in grade 6, they would also be able to tell me the same thing, that, hey, this line looks like it's higher than that line, and overall that these lines have a higher slope than this line. And that's kind of the summary you want to get from figures like this. Don't overcomplicate them if you don't need to. Okay, so last paragraph, or second last paragraph, and then we'll go on to the equation and figure. Okay, so here we have the urea concentration in the sample was calculated from the OD values using this equation. So this is how you get the concentration, right? Because before, what we were doing is just looking at the absorbance. So how do you know how much urea is actually in the sample that you have? You have to work backwards. And in order to do that, you actually have to use a sort of complicated equation here. And here they explain what all of these things mean exactly. And that's important for if you do need to use the equation later on, right? Come back here so you understand what these different terms mean and that you're actually inserting the right values. Because one of the biggest mistakes you can make is just looking at the equation and assuming that N means, I don't know, number of molecules or something, when actually N is the dilution factor. So don't make these assumptions. Always check what they describe the equation to be. Okay. And yeah, the OD blank is 0 for blanks that have distilled water. Okay, anyway, those are what the values are. And lastly, we can go on to this figure. So once again, this is just a description of the that's the equation, and we see over here in this figure, to validate the assay that we did, they did it in the presence of ammonium chloride. So once again, same thing, urea concentration is going from 0 to 5, but this time, are we doing it without any ammonium chloride or with ammonium chloride? And you might be asking, okay, why are they doing it with ammonium chloride? We'll see that later when we get to the questions. But for right now, the more important thing is just understanding the bigger trend, right? That's coming from this figure. So once again, what we notice is overall, as you increase the urea concentration, the absorbance values increase. And yeah, that looks basically the same as what we had before, right? A pretty clear one-to-one sort of relationship. That's great. But more specifically, we want to now look, okay, between ammonium chloride and control, and notice here that they're kind of flipped. So the gray bar is actually the ammonium chloride and the dark gray is control, right? Be wary of that sometimes. What is the difference between them? And overall, even though maybe this is the real outlier, you see that around a urea concentration of 4, that the control seems to give a lower absorbance than with ammonium chloride. But what's key here is that this is not significant. The error bars overlap. And whenever the error bars overlap, that suggests that there is no significant result. Okay, maybe here at the concentration of 3, there is a significant difference between ammonium chloride and control. But what you notice overall is that there's no clear trend, right? At 1, there's no difference. 2, maybe the control is a bit higher. Here, the control is still a bit higher, but at 4, the control is now lower. So there's no clear trend, and the MCAT is not going to play with you that way, right? If there's no clear trend, they're not going to ask you details like that. So overall, what I would say is that there's actually really not a significant difference between the control and the ammonium chloride. Okay, so why don't we move on to question number 1 now, which is basically asking us what a potential issue might be with the enzymatic method for urea analysis. And this is a classic sort of research design or methodology question, which I know a lot of MCAT test takers might find difficult, but the important thing to remember for these type of questions is to just put yourself in the shoes of the researcher, the experimenter, and think of the question from a practical, sort of logical standpoint. What might result if this control wasn't there, or that went wrong, or something like this? And if you have this sort of thinking, these sort of questions go by a lot easier. And I'll show you what I mean with this one specifically. So we see that in this question, the answer choices are basically asking us two things. First of all, is the increased ammonia intracellular or extracellular? And secondly, is that corresponding to a decreased urea concentration or increased urea concentration? And what we really have to think of is, what is the point of these tests, right? The point is to be able to quantify the amount of urea we have based on a sample, because we add the urease and then it produces something. And what we use, if you remember from the passage, right? The passage tells us that the produced ammonia is then measured by a pH indicator, ATP or H2O2, right? The point is that ammonia is used as a proxy for the amount of urea. And if that is the case, then we have to ask ourselves, okay, how could that reading be affected by ammonia, right? And if you really think about it, if all we're looking at is ammonia, and we just assume that all the ammonia that we have in that sample comes from urea, you see where the problem might come in if all the ammonia doesn't come from urea, right? So let's imagine we have a cell where at the beginning, maybe we have 5 molecules of urea and 5 molecules of ammonia. So this is a bit of a simplification, but just hang in with me there. If we have 5 molecules each, and then we add urease, right? So we take these cells, we lyse them, take out the inner contents. So that's already a hint for the reasoning behind the answer choice being an intracellular option and not the extracellular option, because we are taking these cells, we are lysing them, and we're looking at what's inside. It doesn't really make sense to look at ammonia outside the cell anyway, right? Because we want to see how the urea is broken down within the cell. Okay, so if we have 5 molecules of urea and 5 molecules of ammonia, and then we use urease, of course, 5 molecules of urea will be broken down into 5 molecules of ammonia. But how many molecules of ammonia do we now have in the cell? 5 originally and 5 from the urea, so 10 total. And now let's imagine we run this through a pH indicator or something like this, and we find out that, okay, this corresponds to, because we think that every 1 molecule of urea gives 1 molecule of ammonia, that we must have had 10 molecules of urea in the original sample, when that's clearly not true. We only had 5. But because there was more increased amounts of ammonia already within the cell, that led to us getting an increased urea reading at the end, even though that's not true. So that's why the answer here is B. Okay, so I hope that makes sense. Let's move on to the second question. Okay, so now the second question asks us, in the case of urease, so this enzyme that we heard about, what is the mechanism of degradation? Basically, it's asking you, hey, remember this figure we had with the reaction? What's going on here? And if you remember when we talked about this reaction, I told you to just focus on the general bigger picture, right? You don't need to know the mechanism per se until they ask you for the nuance. And in this case, they are asking you a bit more, okay, how does this reaction actually happen? How does this replacement actually happen? And for this, and for any organic chem reaction for that matter, the most important thing is, can you just identify the nucleophile versus the electrophile? And in how I usually see the nucleophile is basically as a compound that has electrons to give. So it has too many electrons, electron density, and these electrons are what do the reactions in organic chemistry, and these electrons will react with an electrophile. And so an electrophile is basically anything that is lacking electrons, and that doesn't mean that it's positive per se, right? Even though a positive electrophile would be great, sometimes it's just that this atom is right next to another more electronegative atom, and that's pulling the electrons away from it. So it's like this sort of polarity. And what a great electrophile usually is in organic chemistry is carbon, and in particular carbon and carbonyls, because the oxygen atom actually pulls away the electrons because it's so electronegative from the carbon, and this carbon becomes slightly positive. And then if we think about water, right? Water is the only reactant that we actually know of here, and we know that the question's already telling us that the water is doing the attack. Water only has electrons to give. It really doesn't have any place to take in more bonds. It's it's happy. The hydrogen, of course, is slightly positive, but it's not going to make any more bonds. So here, the oxygen atom with its 2 lone pairs, right, would be a great nucleophile, and basically always water is a nucleophile. So that's another hint for you that it's going to be A or B. And then the second is, once again, carbonyl versus amine. As I already told you, the carbon atom in the carbonyl is quite positive or slightly positive and would love to be attacked by a nucleophile. And that's the reasoning for A. But once again, for B, right, how can we make sure of that if we don't know what the electrophile is? Well, if you look at the NH2 here, right, that's already an electronegative atom. It's probably not going to be an electrophile. If we look at the how the electrons are distributed, it's pulling electrons away from the hydrogen, so it'll be slightly negative. That's already a bad sign. And lastly, where does the oxygen end up binding at the end? Is it attached to the carbon or is it attached to the nitrogen? You can see here it's very clearly attached to the carbon. So for that reason, it suggests that the oxygen in this water actually did the attack at the carbon and not at the amine. Yeah, you could think that, okay, maybe it attacked the amine, then it pulled it off, and then it reattached, but it's too complicated, right? These reactions have to be simple. So the better thing is that it's a weird sort of substitution, basically, where the oxygen attacks the carbon, and then this NH2 group, let's say, pops off. And now this is the new replacement, basically. Okay, so now let's go on to question 3. Okay, so question 3 finally asks us to use this equation that we saw halfway through the passage, right there. There it is. And thankfully, we don't actually have to do a full calculation with the equation. And what you'll often see on the MCAT is with these more complicated equations, it's not so much that they want you to plug and play and, get some sort of number at the end, but do you understand which values go where? Because that requires focused reading and understanding of what these terms mean, and not just assuming that, hey, N means, I don't know, number of molecules, when it actually means dilution factor, for instance. So just be careful of that, and you'll see that this answer is that this question is actually quite simple, because we just need to figure out, is 0.9 is it 0.9 over 1.2 or 1.2 over 0.9, first of all, and then secondly, is it 150 over 50 or 50 over 150? Okay, and if maybe we can do 50 over 150 first because it's a bit easier, we can notice that concentration of standard in milligram per deciliter is basically already given to us, 5, and that was also mentioned in the passage, so we don't have to worry about that. And the second term now is N, and we notice that N is the dilution factor calculated by dividing the final volume by the initial volume. In general, the dilution factor is always like this. So even if they didn't tell you that, that's just something you should know. And we can see here that we are looking at a 50 milliliter sample taken from a 150 milliliter solution. So taken from suggests that the 150 milliliter was the original solution. And for that reason, it's going to be 50 over 150. So that'll already narrow us down to C and D. And then the second thing is, okay, is it going to be 0.9 over 1.2 or 1.2 over 0.9? Well, we've already narrowed down to C and D, and this is also why I looked at 50 over 150 first, because I knew it would get me down to a simpler sort of choice, because 0.9 is obviously going to be on top at this point. And why is that? It's because the OD sample, right, from this equation is equivalent to 0.9, OD 430 of 0.9. So how do we get the 1.2 though, you might be asking? That's going to be the OD of the standard, right? But if we go to this graph, I don't really see a standard anywhere. I see water and I see phenol red. I mean, we know that we have to look at the 430 graph because that's what the sample is taken from, but which value do we use here? The hint is just the fact that they tell you the concentration of the standard is 5 milligrams. So that means if you were to take a value from here, it'd probably be the one at 5 milligrams per deciliter. And then, is it going to be phenol red or H2O? Well, I can't really tell you exactly why phenol red is there, but you don't need to know that. The more important point here is understanding that this value is nowhere in the answer choice, right? That's what, 0.8 or something like that? That's not going to be the answer. Maybe, it's definitely not. Could be 0.9, and if it was 0.9, then you do 0.9 over 0.9, but then it would be 1, right? It wouldn't be 0.9. That doesn't make sense. So no way that this value is going to give us any of the answer choices here. This does look about 1.2 though, and it makes sense. If you had to pick between these two, then once again, let's pretend 0.9 over 0.8 was an option. It's still better to go with water because water is just, in general, a control almost always, right? And you can see that here as well, right? That's the water blank. And blanks are distilled water, blah, blah, blah. So it just makes sense that you would probably use the value that's given to you by the water curve. So that's why it'll be 0.9 over 1.2, and the answer is C. Okay, so yeah, let's move on to question 4. So the fourth question of this passage is now asking a bit more on the data side, right? A bit more on the passage side, and it requires some reasoning. What I would recommend for this question is to try to just do it through elimination and understand, based on the results that you can see in the paragraphs and the figures, that C is the only one that's actually possible. Because one thing that you might have found really difficult here is the fact that they're talking about color difference. And you're like, color? Where did color come in here? Like, yeah, maybe we saw the phenol red, but how does that actually play a role? What they mean by color in this question is basically absorbance, because if you've ever done a calibration curve or one of these absorbance experiments, you know that when we say more absorbance, we usually mean that the color of the sample changes. So one thing I did in my undergrad, for instance, was something with spinach or something, I don't remember, but like the point was that the concentration, as it increased, the color of the solution in the cuvette would become more blue or green, or I don't remember what it was, but the point was that the color would increase, right? And that's actually the safe assumption here. Even if you didn't know that, right, that's how these experiments work. That's the only variable of interest we're talking about here, is absorbance, or OD. And so if they keep bringing this up and you don't understand what color formation could be referring to or what it's a synonym for, the best bet is to just go with whatever the main variable of interest is. And once again, in this case, it's OD, or absorbance. So it's safe to assume that by color formation, we can just say OD, okay? And with that, I think you'll see why C is the best answer here, because there's significant color difference in the presence of ammonium chloride versus control. Well, we saw in figure 3 that that's not the case, right? These error bars overlap. This is not a significant difference at all. So it doesn't really make sense to call it that. A is wrong. B, dilution of samples in distilled water is not required when using urea samples greater than 5. Okay, what does this mean? That if we have a sample greater than 5 milligrams per deciliter, we don't need to dilute it. But if we go back to this graph, right, what we see is that the concentration of urea only goes up to 5. You can't ever extrapolate calibration curves. And in general on the test, unless you have a good reason to do so, try not to extrapolate from the data, because we can't always assume that the trends we see will hold. And that's the exact same case here. That's actually the whole point, that there is a dilution factor in this equation, is because chances are that the amount of urea in your original sample is going to be greater than 5 milligrams per deciliter. But in order to do this whole experiment, you need to be able to dilute it. So this also doesn't make sense. We kind of have to dilute it in order for the experiment to work. Okay, and then lastly, D, ammonium chloride levels greater than 30 milligrams per deciliter would lead to a significant color difference as predicted by the model. Well, there's nothing about ammonium chloride concentration in here, right? They do mention it in this paragraph as 26.5, but I don't know why it's that value or what increasing or decreasing might do. So rather than just assume something that, oh yeah, it's like super important that we increase it, just don't make that jump, right? Just stick within the confines of the passage and understand that if they haven't told you what it does, it's not necessarily because they assume you have to somehow figure that out. Here, there's really no explanation for why having more ammonium chloride would lead to significant color difference. Because here, once again, we see with 26.5, it's already, there is none. And maybe if we increase it to 30, there would be, but how do we know that? That's really a big jump. And especially if you're not in this field, there's no reason for the MCAT to assume that you would know that. So yeah, in the end, the color formation was weaker in the standard curve. What is color formation, right? OD was weaker in this curve versus that curve. Yeah, that's just true, because we see that the slope is really strong here and the slope here is really weak. Even if you gave this to someone in grade 6, right, they would look at this graph, and if you ask them, hey, like, what's the big trend you see? They don't know what H2 or, they know H2 maybe, but they don't know phenol red, they don't know OD, blah, 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 but they will tell you that, hey, look at the line in A, it's pretty straight, and it's like, and they would probably have learned about slope, so they'll say the slope is pretty big, and in B, the slope is not as big. And that's all you need to answer this question, because in just by like the feel, the sort of gist of these figures, you can see that with A, the slope is bigger, and that probably suggests that the color formation was stronger than in B, and B has the weaker one. So that's why the answer is C. Okay, finally, we're on to the last question of the passage, question number 5. And thankfully, this one is another sort of pseudo-discrete content-based question. In order to answer this question, really all you need from the passage is a small little piece of information. And in this case, we are asked, which of the following is true in the second step of the mechanism of urease? And in order to answer this, and remember, always look at the answer choices before, we see that this is clearly asking us about that Gibbs free energy formula that you might have seen quite often, right? The delta G minus delta G is equal to delta H minus T delta S. So that's when you want to calculate the spontaneity of your reaction, you can use this formula. But on the test, they rarely actually make you use this formula numerically. More so, what they love testing is this concept specifically, the more conceptual side. Do you understand what it means for delta G to be positive or negative? And what is the relationship between delta H and T delta S? And how does that relate to spontaneity? And in this case, remember that we were told that in step 2, it's a rapid and spontaneous decomposition releasing heat energy. So basically all the hints are already in the passage. We are told that it's a spontaneous reaction and it releases heat, meaning it's exothermic. So because it's a spontaneous reaction, we know that delta G has to be less than 0. This is just a rule for the test. And because delta G is less than 0, now the more tricky part is figuring out, okay, does delta H have to be less than T delta S, or delta H has to be greater than T delta S? Thankfully, we're already given a bit of a hint in that it's releasing heat energy. And so because it's an exothermic reaction, delta H is likely to be negative. And if delta H is negative, chances are it's less than T delta S, because T delta S is always positive. You can never have a negative entropy. You can have, you also cannot have a negative temperature. Yes, maybe we do when we talk about Celsius and Fahrenheit, but on the test, T delta S is using Kelvin. So for this reason, that term can actually never be negative. And what this means is that just based on the exothermic part of the passage alone, the answer should be C, right? That delta H should be less than T delta S. But also, because of the way the equation is laid out, this is the only condition that will guarantee spontaneity, because T delta S is always positive. If you have delta H less than T delta S, even if it's positive, right? Let's say delta H is 20 and T delta S is 30. If you put it into the equation, delta H minus T delta S, you'll get 20 minus 30, which is negative 10. And a negative Gibbs free energy is spontaneous. So you see that with this combination of terms, we always get a spontaneous reaction. And yeah, that's it for this question. So with that, we're finally at the end of this passage on urea analysis. I hope you found this dissection helpful and that you were able to gather a few tips and tricks that you can now apply to your own studying. But if you're still feeling a bit unsure, or maybe just want a bit more guidance in Chem Phys or any other MCAT section, one thing I might recommend is checking out the one-on-one mentoring that we offer here at MedLife Mastery, where you'll be paired up with a tutor that can work together with you to find specific weaknesses and help answer your questions in order to get you that dream score that you've been looking for. Other than that, there's a bunch of other resources on the MedLife Mastery website, especially when it comes to Chem Phys as well, so make sure to check those out. And yeah, I hope that your prep is going well. I know it's a tough and long process, but really just hang in there and keep putting the work in, and I promise you it'll pay off on test day. Thanks again for joining me, and see you next time.